So, hello. So let's go to another topics of this lecture. The second important topics is the topics of numerical sets. What does it mean? It means that we talked about sets, but we want to talk about numbers, because this is a course in mathematical analysis, so it is very important to talk about numbers. And numbers form sets, so the first set we will consider is the set of the natural numbers. Then we will pass to discuss the set of integers, that is denoted by Z. Then the third numerical set we will consider is denoted by Q, and is the set of rational numbers. And the last set, which will be the natural environment of our analysis, is R, real numbers. Of course, there is another set which is extremely important, not only from the mathematical but also from the physical point of view, which is the set of complex numbers. And we will meet this set later in our course in December. Okay? So in this lecture we will try to speak of these four sets, and the first set is a set of naturals. This is N. So the question is, what is N? Let me be naive, but I hope clear. N is the set of the numbers 0, 1, 2, 3, 4, and so on and so on. When you count, you use the natural numbers, and probably the historical or psychological development is the reverse. First you count using some sort of numbers, then you abstract these numbers, you call them natural, and you form a set. Okay? And in our treatment, naturals are given by God. In foundation of mathematics, it is not like that. You can construct natural numbers, but for our presentation, naturals are given by God. And so I want to give you some hint about the structure of naturals. You know what are naturals. You know that you can sum up two naturals, subtract two naturals, multiply two of them, and divide one natural number by another one. So there are operations. But let me be a bit abstract. What is an operation? Operations are maps from a set which is n by n, which means a couple. This is the set of couples. Of elements of n, so couple of naturals. So maps from the couple of naturals to n. So let me see on a very specific and very easy example, which is the sum. So what about the sum? About the sum. The sum can be described according to this schema in this way. There is a couple of two natural numbers, n and m. This is mapped by the function or the application sum to n plus m. So nm is an element of n cross n by definition. Then I will talk a bit about this cross. It is not very important, but now just consider the fact that this is a symbol for the couple, for all the couples of natural number, This is the input of our map, and the output is n plus n, which is an element of the naturals. So the sum, you see, the sum is an operation of naturals, which means that it is a map that associates to every couple of natural number one and only one natural number. Okay? So I write it here down. Sum is an application that associates to every couple of natural numbers one and only one natural number. Of course, this way of describing the sum is true for the sum, but not for the difference. Because on the other hand, this formalization of the operation does not hold for the difference. Indeed, if you start from the couple, for instance, 2, 3, and then you want to map them by the difference to 2 minus 3, this is no longer a natural number. So the difference is not an operation in the sense that it is not a map from n by m to n. Okay? So here we formalized, we defined the notion of operation in a way that makes the sum to be an operation between natural numbers and the difference is not. So if you go further, you see that the product can be formalized to as an internal operation in n. When you take the product of any couple of naturals, you end up with a natural. On the other hand, the ratio cannot. Okay? So this is just a sort of fundamental introduction to try to convince you that for me, the operation allowed in n, so we can say that n is endowed with two internal operations. Sum and product. Okay? And the sum and product have some properties. And now you start understanding that for me it is very nice to introduce a structure and then to list the properties of the structure. This is a typical mathematical attitude, okay? Not a very engineering attitude, but the following properties. First properties is associativity. So associativity means that if you have three numbers n, m, and k, and you first perform n plus m and n plus k, the result is the same as first computing n plus k and afterwards summing n. This is associativity, and it is the same for product. For instance, here you have that n dot m dot k is equal to n dot m dot k between brackets. And associativity, as it was for logical connectivity and for operation between sets, is the property that allows you to get rid of the brackets. So you can directly write m plus k without brackets to denote what to do first, because it is irrelevant. Whatever you do first, then the result is the same. And here it is the same, n dot m dot k. Okay, this is associativity. Second, commutativity, which is probably the most popular between you, because it is really simple. You have that n plus m is equal to m plus n, as well as n dot m is equal to m dot n. Okay? And the third is the distributivity. The distributivity is the following properties: n times m plus k is equal to n times m plus n dot k. Okay, you know this holds. This is basically all the list of properties, and there are some others seem to be stressed, and the fourth property is the existence of the neutral element. So there exists an element A in n such that n plus A is equal by commutativity to E plus n, which is equal to n. This neutral element is denoted by 0, and there exists an E prime in n such that n dot E prime is equal to E prime dot n is equal to n. And this E prime is denoted by 1. Okay, you know everything about that. And this is all for the algebraic structure of naturals, but there is another property of naturals which is extremely important, because it gives us a powerful tool in order to provide definitions and also to provide proof. And this is the induction principle. Let me use the red here. This is really what makes interesting the structure of n, what characterizes the structure of n. Of course, n is not the only set that respect the induction, but it is the smallest one, it is the most essential one. So let me explain it, okay? There are many ways to introduce it. I give you two ways. First is let T a subset of n. This is probably the clearest from the point of view of set theory. A subset of n such that first 0 belongs to T. Second, provided that an element n belongs to T, then the subsequent element n plus 1 belongs to T. Okay? there are these two features, and then the conclusion is that the set T is equal to n. Okay, the reason is quite clear at our level, because 0 belongs to T by 1. Then by 2, if 0 belongs to T, then 0 plus 1 equal to 1 belongs to T. So this is for point 2. But again, using point 2, if 1 belongs to T, then 2 belongs to T, and so on and so on. You see from this intuitive process that every natural number belongs to T. This is another version of the induction principle, which is very used, is the following. Let P of n be, as a logic I would say a proposition of natural numbers, but let me say a property of natural numbers. Then, if P of 0 is true, is verified, first, second, and provided that we have P of n, then we have P of n plus 1, then the property P holds for all naturals. So in books you find both versions of this induction principle, and you immediately see that it is the same, because from the second you have that you have this property of naturals, P of n, so you can say that T is the set of the natural numbers enjoying the property P. And then you have as a hypothesis that 0 belongs to T, and then if n belongs to T, then n plus 1 belongs to T. And then the property P holds for all naturals. Okay? Why is this principle that seems to be so obvious, why is this so useful? Basically for two reasons. First, to give rigorous definitions. For example, trying to define the factorial n factorial of a natural number I know you could be tempted to write n factorial is the product of n minus 1, n minus 2, many dots up to 2 and 1. So it is the product of all numbers from n1 up to n. This is the factorial, grows very fast, faster than the exponential growth, and so on and so on. Good. This definition is very clear, but for a mathematician it is awful. And not because it is very clear. We like clear definitions, we like clarity. But because there are these dots, they are not a rigorous mathematical symbols. Okay? So this is not rigorous. And the rigorous version of this definition uses the induction principle. Let me see why. First, we say that 0 factorial is equal to 1, which is indeed not really included in this formal means not rigorous definition. We have to establish that. We have to define it. It does not come from other definitions. Second, n plus 1 factorial is equal to n plus 1 dot n factorial. So here we define the operation factorial on n plus 1 starting from the operation factorial on n. And here we use the induction principle in the sense that with these 2 steps we define the factorial for all natural numbers. And this is rigorous this time. Okay? We will see when studying sequences, we will see the sequences by recurrence. So, the first use of induction principle is to give rigorous definitions. But the second, probably most important, is to give rigorous proof. In order to illustrate this point, let me consider the problem of Gauss, aged of 8. When he was 8 years old, he was at school, and the teacher was not happy that day. He wanted the kids to be calm, and he wanted probably to read the newspaper or to look at his smartphone or Facebook or Snapchat or Instagram or so on. So he told the children to sum up all numbers, all natural numbers, from 1 to 100. So he was sure to be safe, to stay there half an hour and more with the kids working, but he underrated his young Gauss, who in some seconds gave him the correct answer. And this is how Gauss made 1, 2, 3. So consider all numbers up to 100. So what Gauss noticed was that if you consider the first number of the list 1 and the last one 100, you obtain 101. If you consider the second and the second last 2 and 99, you sum up, then you obtain 101. The third and the third last 101. So Gauss discovered that you can reorder the numbers from 1 to 100 in couples. How many couples? Of course, they are 50. In 50 couples, whose element summed up give 101. Then the answer to the exercise the answer is 50 times 101, and this is 5050. And this is the correct answer. Okay? And this is what Gauss told the teacher. The teacher apparently was not happy, but in reality he really appreciated Gauss. He gave him the possibility to study, because Gauss came from a very poor family. And so if you read some books, some biography also of Gauss and some movies about that, it is always said that the teacher beated Gauss because he was not happy at all of the fact that this guy was so clever. But this is really a romance. It is not true. However, this is the result. It has nothing to do with induction up to now. Where does induction enter? So first, try to generalize to the sum, not of the first 100 numbers, but to the first n numbers. Start with n even. So you can do like Gauss, 1, 2, 3, and then many dots, n minus 2, n minus 1, n. And again, you collect in couples, n plus 1, with the first and the last, and the second last, n plus 1, because it is n minus 1 plus 2. Then you have n minus 2 plus 3, and so you have n plus 1. And again, the sum you are looking for is n plus 1, which is the sum inside any couple. And how many couples you have? You have n divided by 2. Okay, so this is a formula with n generic. If you put n equal to 100, of course you have 101 times 50 like before, and you end up with the same result. And then if n is odd, you can do as you want, but the trick is to, because why odd is different? Because you have to form couples. If you want to close off couples, you need an even quantity of numbers. So here in this case it is odd, and here you have n minus 2, n minus 1, n. But to make it even, just add a 0 here, so you can form couples. And so here you have n, here you have n minus 1 plus 1, n. So this time you have how many couples? The sum is n, which is the sum inside any couple, times what? How many couples do you have? Here you have n plus 1 numbers, because you have not only from 1 to n, they are n, but you also have the 0. So the couples are n plus 1 divided by 2. And notice that the formula is the same. So these are general formula. We did not find them We didn't find these formulas by induction. We found them through reasoning, so-called heuristic reasoning. Heuristic means not completely rigorous reasoning, which allows to find a result. Okay? Eurisko in ancient Greek means I find. Heuristic, that is done to find. But once you find them, you can use induction to prove them. Is the rigorous tool to prove this formula. But I stop here, and it will be the next step.